Welcome everyone. Today I would like to speak something called a lemma. We all are familiar with theorems, but what is this lemma? What's the difference between a lemma and theorem? Lemma is a subsidiary or intermediate theorem in arguments or proof. Here I am going to talk about Schwartz-Zippel lemma. It is actually a part of complexity theorem. It's observed that solving polynomial equation is hard, and so you may be able to solve it approximately only, or you just can't say a probability that is true or not. Schwartz-Zippel lemma comes in complexity theorem, in particularly what is called PIT, polynomial identity testing. So we have polynomials here f and g. Number of variables doesn't matter, and you want to check whether they are equal or equivalently, whether the difference is zero polynomial or you want to check a polynomial is a zero polynomial. This is not very easy because lot of polynomial automatically might come in discusses in some sense. So that is the first problem. Let's say as determinants of some matrices or something like that, it might not be absolutely obvious from the first glance the two polynomials are same or not. So we have the two polynomials f and g here, but we know that they are same. X1 minus x2 into x1 plus x2, that is actually equal to x1 square minus x2 square. But even if they are equal, one needs to factor f into monomials to see this. So factorization certainly a process which you might not be able to do well. In this case, of course you can, but imagine a huge polynomial there where you cannot do it. So regarding complexity also, while factorizing polynomials is costly. That is for the first time it was O of n, and after factorization into monomials it becomes O of 2 raised to n. So complexity turns from polynomial time to non-polynomial time. That is, the problem turns from tractable to intractable. Tractable means it is in polynomial time. The complexity comes in polynomial time, or it is intractable means it is in non-polynomial time. So factorization is not advisable, or it's not an optimal strategy. So here comes the lemma. Let's have a look at the statement or theorem. So you have polynomial of a certain degree. Let's say it's not a constant polynomial with coefficients in some fields. The fields doesn't matter at all. You choose a subset. This is order of yes. You can choose. This is order of s. Here you can see this is the order of s. Like it is written as determinant of s, it is the order of s. Order of s is the it chooses a for the chosen subset s. You have found roots. As I said earlier, the roots are not exact. Only a probability or a certain choice from the subset is a root versus probability, or d over s. Here we can say it d over s. You always have these upper bounds d over s, which is actually easy to compute. So it's basically cuts for free. Then you have this funny extra additional here if f is non-zero. If f is non-zero. That is the theorem says the polynomial f a degree with greater than 1 with coefficients of some field k, and k is a subset or f s, and from this s we have randomly chosen r1, r2, etc. rn, provided f is non-zero. This is actually funny itself. Here welcome back to the question. Here also we have the previous question comes around. How can we actually check whether the polynomial are same or not, or the polynomial is zero? Well, just repeat the whole process. Repeat the whole process k times. We can say that if you get k times in a row 0, this happens very rarely. So d over s, if f is big, let's say s is really big, that d over s, the k get very fast to 0. So it gets more unlikely that this always holds, right? But now come the point. Let's say you have a polynomial and you really want to know whether it's 0. You just throw in a few roots and you get 0 all the time. So it can be almost certain. This is a kind of the converse of the theorem. Then you can be almost certain that it is constant 0. So to find a 0 polynomial, just take your favorite field first, or finite field, favorite finite field, for example, or actually any s, any field you want to throw it, evaluate it at few points. If it spits out 0 often enough, you're almost 10% certain that your polynomial was 0. Here comes the application of the theory. Here we have a graph G with an even number of vertices, say 2n. A perfect matching of G is a choice of n edges such that every vertex of G is an endpoint of exactly one of the edges. The natural computational problem for matching is here, like given a graph G, how effectively we can determine whether there is a perfect matching of G. Second one, find a perfect matching if one exists. This section will describe a probabilistic theorem that solves a problem using the Schwartz-Zippel lemma. Here we have given such a now look here, polynomial that governs the existence of preferred matching turns out to be determinant of a certain matrix defined below. First, what we are doing is we are making this graph into a matrix. Each entry in the matrix, that is the Tute matrix of G, is given by certain rules. That is, Aij is equal to Xij if Vi and Vj share an edge and I less than j. Or its entry is like minus Xji if Vi and Vj share an edge and I greater than j. Otherwise it is 0. So from this Tute matrix we can have there is a perfect match of G if and only if the determinant of the Tute matrix is not the 0 polynomial. So that's all about the topic. Thank you for watching me. Thank you so much.